Okay, so we'll be live in 10 seconds, okay? Just count to 10 and start.
Okay. A very good morning to all the participants and the distinguished panel, and welcome to the third day of the International Conference on Graph Labeling and Application in honor of Dr. B.D. Acharya. Our chair for today's session is Dr. Tarkeshwar Singh. He is the Associate Professor in the Department of Mathematics, Birla Institute of Technology and Science, Pilani, KK Birla Group, Goa campus. I invite you, sir, to take over this session.
Okay. Thank you, Stephanie. And
Yes,
I'm very happy to introduce my guru brother, Dr. Gajendra Pratap Singh, who is the assistant professor in the School of Computational and Integrative Science, Jawaharlal Nehru University, New Delhi. He got his PhD degree from Delhi College of Engineering. Now it is known as Delhi Technological University in 2013, under the guidance of Dr. Sangeeta Kansal and Dr. Mukti Acharya. And his area of his specialization is petri nets, graph theory, and analytical hierarchical process. He is associate editor of many journals. He has finished one DST-sponsored project and got a Young Scientist Award in 2017. Currently, he's guiding one JRF and one also he's guiding, mentoring one research associate and many master's students. So, and we are very much associated with each other. So as I told that Gajendra's first approach to Madam for PhD degree, and Dr. Acharya has given a book to read and told that first we go through that one, you can publish many theses from that. Then Madam Acharya, at that time, I think she was about to retire. So Dr. Sangeeta Kansal requested to become one of the guys.
I retired after his defense.
After my
After his, I retired after his defense.
Yes. Okay. So Dr. Whole work was under with the guidance of Dr. Mukti Acharya and B.D. Acharya, but Dr. Sangeeta Kansal was also faculty in the Delhi Technological University. So she was also one of the official guide. So with this remark, I just request Dr. Gajendra Pratap Singh to start your lecture.
I hope Sangeeta will not get offended.
Thank you, sir. Thank you very much, sir, for giving me an opportunity to speak in this conference in the memory of Professor B.D. Acharya, sir. Thank you, sir. Thank you very much, sir. And also thanks to organizer as well as Professor Jessica. And before that, I would like to say something about B.D. Acharya, sir. B.D. Acharya, sir, is one who taught me the lesson how to read the research book, good books, and how to do the research. Basically, Professor B.D. Acharya, sir, is the father of my brain, and Acharya ma'am and Kansal ma'am are the brain of mother of my brain. Thank you, madam, for giving me the opportunity to work and interact with the B.D. Acharya, sir, during my PhD 2007 to 2013, 12. Thank you, ma'am. Thank you very much, ma'am. Although sir is not around us, ma'am, but whenever I start reading books and start guiding to my students, he is always around me, and I feel that he is sitting in front of me, and this gives me a very good kick to start better and better in my life, and that is why I able to do many things with the blessing of B.D. Acharya, sir. During my PhD, I joined in 2007 December, 10 December. I came from the rural area, from district Bijnor, village Tripura, from UP, Uttar Pradesh. From there are lack of facilities are there, lack of library infrastructures are there. Then I moved to Jamia Millia Islamia. I did my master's. Then I cleared the examination, entrance examination, and get the admission and DTU. And first 6 months, I will be the touch in Professor Sangeeta Kansal. Then Professor Sangeeta Kansal and Acharya ma'am jointly supervised me, and basically uh, all the work that I complete and done during my PhD will be done at the Acharya ma'am home. And in a week, 3 to 4 days every day I used to give my presentation 5 to 6 or I was standing in front of board, and I literally Professor Acharya sir suggests me two books. One is Frank Harare Graph Theory, and another is Peterson, J.L. Peterson. That was the first book, and Rizik, and another monograph, Springer, published by Springer. Then I worked and I sold literally 5 chapters, and I got many problems, several problems. And the concept that I going to introduce here, given the problem given by Professor B.D. Acharya sir, crisp and Boolean pectinate. I solved only the one problem, and my PhD thesis is submitted. And after that, after submission of my thesis, I joined JNU. Then I did a project on some advances in Boolean pectinate. That means this shows that there are a lot of scope after submission of my thesis. Even one problem is can produce by BDHRSN can produce many PhDs. My students also working for the generalization of Boolean pectinate, and one more student working on the applications area. So I'm really thanks to Professor B.D. Acharya sir and Acharya ma'am. Thank you very much, ma'am. Thank you, ma'am. Now I'm going to sharing my PPT here. So today I'm going to discuss and delivering a talk on Boolean and crisp Boolean pectinate. This is some outlines of this talk. First of all, how to start the work for the in pectinates for the beginners, and some backgrounds, and why and what pectinate dynamics, then property. Then after that, I will discuss some with some example the theory of Boolean pectinate and crisp pectinate. Anybody can start work in pectinate theory by in this sequence that will feel more easy if they follow the sequence: basic introduction, fundamentals of pectinate and theory, diverse application, analysis techniques in pectinate, classification and types of pectinates, and research scope. After that, we can find many research scope if we follow that sequence. In fact, this concept, pettinate, is introduced by Carl Adam Petty at the age of 13. Then he was the 13 years old. And officially, the existence of this concept came in 1962 when Professor Carl Adam Petty submitted his thesis on communication with automata to the Damas University in 1961, and defended his viva in 1962. Originally, he defined pectinate either arc is there between two different types of nodes, or not there. If it's there, value is 1, otherwise value is 0. But there are a lot of history there, and there is no formal definition of the pectinate. Uh, there are so many variations in the definitions of pectinate due to the various time zone and various requirement, and different diverse applications. And here in this entire talk, I will follow the definition of called Jensen. Jensen definition I will follow throughout that discussion. These are some references, and Holt, Patil, Winskill, and Murata is also one of the good patinate. He worked very good work in this area also. What are the patinate? Basically, patinates are the mathematical tools, or you can say it is a discrete event-driven dynamical system. Patinates are formal formal, we can also see as a formal graphical executive techniques for specification and analysis of concurrent discrete event dynamic system current,
Yeah, yeah.
and why patinate. As we know that there are so many systems in our day-to-day life that we cannot study directly. So here, patinate is the main source, or you can say we can get some idea how to study or how to get the idea to start work in these areas, because these type of areas, astronomy, nuclear physics, sociology, biology, computer, very complex systems. So if we use patinate theory to applied to study these areas, then we can get many informations. There are diverse applications of patinates in many areas, networks, in as a pure mathematical models are also there in the literature. Mathematical model in the form mathematical model, biological sciences, social sciences, decision making, visual communication, and these are the pictorial representation of a patinate. Here, in fact, patinate is the directed bipartite graph. Here we have two types of nodes. One kind nodes is boxes. Boxes are the transitions. Transition generally we can take as a, wherever we are doing modeling. Actions are generally the transitions. Action or any kind of activity we can denote as a transitions. And second time nodes is place or circles. Place denoted by circles, or circles are the places. Generally places are the constant things or stable things we can take as a place, and dot inside the place is the tokens, or token represents some kind of information that is available of inside the place, or resources you can say. And arrow represent the flow relation, maybe the boxes to circle, or circles to boxes, any direction. If flow is circle to boxes, the flow is known as positive flow, otherwise it is negative flow, or we can say inflow, outflow. These are some elements. This is the definition that I'm going to use here. Johnson gave this definition 1986. This is more operative definition because it can be represented expressed as a matrix form. Matrix form. A patinate is a 5 tuple consisting of 5 elements p, t, I minus I plus mu 0. P is a non-empty set of places, is a non-empty set of transitions, and intersection is empty. I minus I plus is also a function from the Cartesian product of places and transition to assign a natural number including zero, and are known as I minus known as negative and I plus known as positive incident functions. And for every place there exists a transition. That means no place can be, or transition can be isolated. And if there is a relation between transition to transition, that will be by a place. We cannot directly connect to transition to transition. Similarly, place to place. If place to place is connected, that has to be connected by a transition. And 6 number mu naught is the initial marking, that means place can hold any number of tokens. It may have in very large number, just like a natural number including zero. That is the definition. So here I minus I plus generally is the number of arcs from place to transition, and I plus is the number of arcs from transition to place. In and matrix form we can also express I minus as a p cross t cross 1, and t cross t cross 1, and p cross t, and t cross coordinate of t cross p. Next, in general, a marking mu can hence be represented as a vector. Mu belongs to n power n, where n is the coordinate of place, such that ith component of mu is the value of that particular place, particular token. That means number of token at that particular place, pi. The state of patinate is defined by its marking or change of state. This is very simple example. Here we have 3 places and 4 transitions. Place P1 consisting of 3 tokens, hence we can write in this form mu naught P1 is 3, mu naught P2 is 0, there is no token, that is why it is 0, mu naught P3 is 1, the token is 1, and this marking by this definition, mu belongs to n raised power n, can be represented as a vector form. That means this first component represents the number of tokens dot present in the place 1, and second component represent number of tokens, that means no token, 0 token. Similarly, third component in vector form. This is the illustration for the patinate structure and patinate graph. These are the figures. The figures are the patinate structures, and the representation of these patinate structure is called patinate graph. This is the patinate graph of these patinate structures. Here 4 places, 4 transitions are there. So here I P1 T1 are the elements of I minus. That means arc from P1 to T1 is 1. P1 to T1 is 1. It is here. Similarly, P2 to T1 arc is there. P2 to T, that is also elements of I minus. I plus means T1 to P1. T1 is this is T1 to P1 element is there. That is, this is a expression or patinate graph of this patinate, these structures. Whenever we are doing modeling, we can have transition, maybe event, computational steps, process, any kind of process, any task, job, logic, implication, process, and input output place, maybe precondition, output, and post condition, output data, input data. In this way we can take for the modeling. Or other interpretation we can have like these places, maybe sometime buffer, channels, any geographical locations, condition or state. Transition generally events, transformation, transportation, any kind of activity may be the transition. And token generally represent humans, goods, machines, and generally token define or used to define the execution of patinate. That means how the one state it changes for a given state, that we can see with the help of marking or tokens. So here is the how the movement of token is work. Then we can have a rule that is called firing rule or dynamical system, dynamical rule. Sometimes we call it, or sometimes we call it transition enabling rule. So suppose n is the patinate, is the 5 tuples. Any transition T is set to enabled at the marking mu if and only if number of arc from place to transition is less than equal to number of token that particular place, and this should be true for all the input place that are connected to that as the input place as that particular transition. If the transition is enabled, it is up to the decision maker or probabler define that the person or the researcher, then he can or he or she can fire the transition. Enabling transition doesn't mean that the transition is fired always. It is up to the event, up to the totally depend on the if the event actually take place, then we can fire. Otherwise, transition is there, it may be enabled. Enabled does not mean the firing. After firing, suppose transition is enabled and you want to fire and event actually take place. After firing, the new marking, let us suppose mu dash, can be expressed as mu p minus I minus arc from place to transition or transition to place, that we have to calculate for every place for this. This is the dynamical rule. For very simple example, we have 2 places and 2 transitions here. So here we can see transition T1 and T2. Here both transitions are enabled. Why these transitions are enabled? We can see for with respect to the transition T1, the arc from place transition to P1 to T1 is 1, and number of tokens in that particular place is 2. 1 is less than equal to 2. That means transition T1 is enabled. That means that transition is enabled and may fire. Suppose transition T1 is fire. Now what will happen after the firing? Similarly, T2 is enabled and we can fire if we want. And let us suppose at this stage, initial state is 2, 0. The marking in the place P1 is 2 and P2 is 0. 2 and 0. So here 2 and 0. After firing, when transition T1 fires, then the new state of the system is 2, 1. That means number of arc number of token in that place P1 by this rule is the initially is 2 minus arc from P1 to T1 is 1, arc from T1 to P1 is 1, 2 minus 1 plus 1 is 2. The token remains same. And for place P2 is number of token in that place P1 before firing is 0. 0 minus 1 plus 1 is here there's no for this there's no arc from P1 to T1 this one, that means token is 1. So here the new marking after the firing 2 comma 1, this is the new state. Similarly here the new state is 0 comma 1. Here we can also check here if the transition T1 or T2 further fireable or not fireable. If we check here, so we can see transition T1 is fired at this stage. If it is fired at this marking, the new marking is 2 comma 2. Similarly, if T2 fire, the marking is 0 comma 2. In this way, we can have all possible states. All possible. Here we have 6 states. After if we check this, the state is after firing of T2 is 0 and 1. After that there is no firing because no transition is enabled by this rule. So here the system is dead. Deadlock occurs. That the final state is of system. This state, this is directly reachable from the initial state or initial marking, and this is reachable from this state by subsequent firing of the transitions. And this is also reachable from this state. And this state, the firing sequences, if we talk about by this state, if you fire a T1, T1, T2 firing sequence, we can also find the firing sequences here like this. So this is what that I have already explained, the firing sequence. And now another example, we can model some chemical equation S2O release. This is S2C, CH2. I think this is CH4. We can model like this. This can be modeled, but I will show one more realistic example in the next slide. That is why I'm skipping the slide. Before that, this is the petri net, and this is the reachability tree. That means we can express these all possible state in the form of tree also, where the nodes are the marking. Nodes are the marking here. So here the initial marking is, we can see 2 1 place P2 consisting of 1 token, 2 1 and 1 1. Initial marking is this. At this stage, initial marking, all transitions are enabled. If T1, T2 and T3 are enabled and ready to fire, if T1 fire, we have 200 by the firing rule. This is the new marking, new state of the system, and this is also new state when T2 fire. In this way, we have all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible states here. So this, the representation of the entire phenomena, this is called reachability tree, where nodes are labeled as the marking and directions are also there, directed reachability tree, you can say reachability tree, and or sometimes cycles are also there, then it is called coverability graph or reachability graph. But here there is no cycles here, so it is called reachability tree of this petri net. Then we can analyze the power of the petri net. By the given very small subnet, petri net, we can generate all possible states in very by writing some code. If somebody is expert in writing on code on any kind of platform, then we can solve many problems. Similarly, just like a diagram, we have a self loop concept here. If a pair of a place P and the transition T is called a self loop, if P is both input and output, for example, like this. This is a self loop. Self loop generally used to modeling the chemical equation whenever we have catalyst equation. As we know that the property of catalyst is it never destroy or created. That means if we have one token here, by the firing rule, the token always remains constant. It cannot be destroyed or created here. That is why we can use the self loop concept to at a time of modeling in the chemical equation, that element. One more definition, T in terms of pre and post set. T pre is the set of all places, that means arc from place to transition if it is greater than 0. It is T pre, T post. Similarly, P pre we can define. For example, here T pre means this is T1 here. T1 means how many places are connected. P1 and P3 is connected with T1. That is why it is P1, P3. Just, and we can also express this pectinate in the form of incident matrix, incident matrix, just like a graph theory, digraph theory. So here I plus and I minus, there are two types of matrix, and the difference I plus minus I minus is the incident matrix. I plus is the positive incident matrix. How we can construct the positive incident matrix here? So here arc from T1 to P1, T1 to P1, T1 to P1 is 1. Similarly, T1 to P2 is 2. To wait 2 means arcs are from T1 to P2 is 2 here. So here then we can express all these positive incident arcs, outgoing arc in the form of positive incident matrix. Similarly, negative incident matrix we can construct, and if we take the difference, we can have this is by typical mistake, I plus minus I minus. This is the incidence matrix. So here there is a problem for the researcher. For a given incident matrix, how many pertinates are possible? That is also a challenging problem. Anybody can try for this, for the given incident matrix. Similarly, we have in the, just like a graph theory, we have source and sink concept, just like this. If we have all the directed arc towards to the transition, that is called, this is called sink transition. And if the outgoing arc are there, that is called source transition. The very important property of the sink and source transition is that if you have token in the sink transition, in the input place of the sink transition, the token always consume. It cannot be exceed. It always consume by the firing rule. If the token in the output place, the transition is unconditionally enabled, and they are exponentially growth of token or in the reachability marking. In that case, this is also still open problem, but solution is given by the one solution, one algorithm is given by how to make infinite tree to the finite tree by the in the form of coverability algorithm is there, that I have seen in the Murata paper, that is given in that. There are some applications that very realistic applications. Suppose you want to model the chemical system. Suppose we have three equations. That is also that the source is taken from the Google, but this modeling done by here like this. If carbon and oxygen, that means here equations are the transition, and the atoms, carbon and or molecules are the places, and token represent here the availability. That means this particular carbon is present. It does not tell about the how much quantity is there by the ordinary pertinent, but we can, this token represent the presence. If carbon and oxygen presence are there and combines with this equation, that it release the token, it release the CO2. CO2 means the token move from here to here by the firing rule. It doesn't mean that the token 1 plus 1 goes to the output place 2. It doesn't mean that. It is not the case here. By the firing rule, we will have the one token here, like this. The token is here, the token is consumed from the input place here. Similarly, when NOH and CO2 combine each other, the transition and some reactions are there, then this token will consume here, and this NOH CO3 released from here, like this. Similarly, the entire equation we can model. If we have many system of equations, so many system of chemical equation, we can model, we can easily illustrate, we can easily, that can be easily understandable like this. We can also use the pectinate concept in that concept of computation and modeling. Suppose a very simple expression, if you want to model, that can be also modelable here. We can model like this. Now, there are two types of property in the concept of ordinary pectinate or very simple pectinate: behavior as well as the structural property. The behavioral properties are those which depend on the initial state or initial marking of a pectinate. Initial marking plays a very vital, important role. And the structural property on the that does not depend on the initial marking. That means it basically depends on the topology. What kind of structure we are using here? It totally depends on the structure. That is why it is called structural property. All the diagram properties, maximum property, not all, we can analyze here in the form of structural property. This is the behavior property that I will use in the to defining the crisp and Boolean pertinent boundedness. A place pi of a pertinent is k bounded if every mu dash belongs to R and C. R and mu naught means reachability. It is a reachability set of all reachability marking from the initial marking such that mu dash pi less than equal to k. That means a place, a pertinent is k bounded if all the places in it are k bounded. And generally boundedness property is useful when we want to define the size of system or absence of overflow. If you want to show the absence of overflow, we can use the boundedness property. So by this, I am motivated by this bounded property. Then at that time, and with the discussion with the Professor B.D. Acharya sir, then he told that if we, why don't you put k equal to 1? If we take k equal to 1, basically it becomes one bounded. And one bounded here, the concept which is called here safe pertinent or safeness. If we have 1-0 sequence, then we initially that I will show the next in the next slide here. So then we will study the one safe pertinent. Now deadlock is also there. It never fire transition in deadlock. So here we can see this is the pertinent given here. The place P1 has 3 token. So here this is the reachability tree of this pertinent. So here we can see there's no every marking maximum component is in that is 3. That means that is why it is called 3 bounded, and this at this initially state it is the place P1 is 3 bounded. Overall there's no token more than 3 here. That is why it is 3 bounded pertinent. Safeness. A place in a pertinent is one safe or safe if the number of tokens in the place never exceed 1. A pertinent is one safe if all places are one safe. It is also sometimes it is called one bounded pertinent. Now this is the example of the traffic light system. I'm leaving that slide. This is the safe system. Lights are the signals are the places, and the start of the activity lights are the transition. Green represent the this already existing green light is there here. Then if yellow start of yellow is there, the token move from here to here. That we can express for we can also model more than 2 traffic lights for the very simple illustration for the one second. Now come to the Boolean interest pertinent. By using this, the property of safeness when the token never exceed 1 for every place. So the idea is coming from the star graph. Basically, star means everybody knows about the star. Then we subdivide the edges and vertices of the star graph K1n. The central transition and the pendant nodes are we subdivide like this. We taken as a transitions, and the subdivision of the arc or edges we divide we taken as place node. Suppose we have K1n as K1 means center nodes are transitions and all pendant nodes are the transitions, and subdivision of the arcs as the places, and we orient like this as shown in that picture. Place P1 place P2T to the pendant nodes and all the central all arcs from the places to the central node. So this is the first pertinent. We call it as a one safe star pertinent SN. SN means it has n places and n+1 transition, including the center transition here. Then then after that, then we found some result here. That means this if we fire all the transition, we have all the binary n sequences, all the binary sequences 0, 1 sequences. Possibly sometimes it is repeatedly or in the form of exactly ones. Then we define two types of patinates here. One say patinate that generates all the binary n vectors as marking vector is a Boolean patinate. One say patinate generates all the binary n vector as marking vector, possibly with repetition is there. And Chris Boolean patinate is the patinate, once a patinate that generates every binary n vector exactly once, no repetition allowed. And we define as a Chris Boolean patinate. This is the example of the Chris Boolean and Boolean patinate. If we take this patinate and if we fire all the transitions, all transition enabled here, I'm not talking about the marking. We will have condition under what condition the what should be the initial marking. So that if we fire all the transition, this reachable tree consisting of all the binary and sequence, the repetitions also there that is given in the reachable tree. And this is the patinate. It consisting of all the binary sequences. That means here 3 places, 2 raised power 3, 8 binary sequences are there of length 3. All are distinct here. And this is the Chris Boolean patinate, and this is the Boolean patinate. Then here, whenever we have this, we first we have shown the existence of the patinate that generate all the binary and vector as its reachable tree, and this is the first one. That then after that we motivated that we thought that what will be the initial marking, what will be the size of places and the tradition, that we generalized or we got some very interesting results based on this. Then we proved that for any Boolean patinate, Boolean means any once a patinate generate all the binary vector is in its reachability is called Boolean patinate. Mu naught P is equal to 1. That means if we take mu naught equal to P, that means if we take all marking initially is 1, 1, 1 for all the places. Then if the patinate is Boolean, the mu naught is always 1. Reverse condition we are not able to find, but it is also a still problem.
Pressing plus 3 more minutes.
Yes, sir. Yes, I will conclude it. Okay. Then after that, based on this patinate, we define that the reachable tree of Sn with 111 as initial marking contains every binary n vectors a1, a2, ai belongs to 0, 1. Then after that we remove the central node and at tn plus 1 transition here, still we have a patinate then which is called disconnected patinate. If we remove the central transition, and we found that this is also Boolean patinate. And if we arrange and we have defined some homomorphism of the patinate, and we found that a disconnected patinate whose homomorphic image is complete Boolean lattice by if you fire some use some tactical some strategic firing sequence like this. I'm just time is short, so that is why I'm leaving some slides here. Suppose this is disconnected patinate for 3 places, and if we strategically fire, then we will have this. This is the complete Boolean lattice, and this is the reachable tree of this. I have not shown here. Somehow it is missed here. But if we take the homomorphic image of that reachable tree that is not shown here, then that will form the under some definition the complete Boolean lattice and dimensional complete Boolean lattice. That is also published somewhere. Paper in IEEE like this. After that we found some other patinate minimal. That means should there exist, we thought that if there exists any patinate, that means firing sequence is minimum in the sense the length of firing sequence is minimum, depth of the reachable tree is minimum. Then we found that this patinate by under these constraints are there. Then we found that for n is equal to 3 places and 7 transition, then and if we fire of all the transition, then we will have star. We generalize that, and we found that, and we proved that along with Acharya sir, guidance Mukhya Acharya ma'am, Dr. Sangeeta Kansal ma'am, that this is the star graph, downward star graph, and this is unique that we have already proved. And after that there are so many results I have not shown here, But in the last one, we have gave a theorem, embedding theorem. That means every one safe patinate can be embedded into a Boolean patinate. And this patinate, we have we named that theorem. And the last, whenever I submit my thesis, frustration theorem. We were all are the frustrated that we had not with some result. Then we called it frustration theorem as well. And this is very wonderful result we got that. And we have so many open problems as well. Uh, and some of the group that is working right now with the blessing of Acharya sir is there. And thank you very much. And I want to show one more thing. Can I show Tarkeshan sir? Hello sir. Can I show? Can I take 1 more minute, sir?
Yes, you can.
Okay. Yes, sir. Now, just a minute. I just wanted to share that. Is it visible, sir?
Yes,
So
coming.
there are many software available in the literature. Let us suppose I just showing one example here, and we are also trying to write a code for and almost more than 50% condition we have already defined. Suppose this is the patinate, very simple patinate, and that means I want to show that how the exponential growth is there if we make minor change in the token. Suppose if we put one token here, one token here, one token here, and if you run it, you can see the changes here. And if we generate the reachability, coverability tree or reachability tree, then you can see the tree. This is the by coding we can have. And if we change my very small change in the marking, let us suppose if I do the change here, if I increase the tokens, let us suppose if I increase more token, let us suppose 3 or 4, then you can see the how exponentially growth is there in the states. You can see it is you can see the very exponential growth are there if we the minor changes is there. So that is why it is very important, because for a given that will also save some time. If for a given very small network, for the very small network, we can analyze the very huge network, very huge networks. That is
But
a big
that network is not being shown, which you are getting after firing this one.
okay ma'am. Okay, I will show you, ma'am.
It is
Wait,
not
ma'am.
coming.
Okay ma'am. Yes ma'am, I will show you again. It is there, ma'am.
We show with 1 and 2 token, that will be
Okay, this is the ma'am. This is the network. If I change the token 1 to 3, very small. If we have 3 places, 3 transition. Now look, we can see how the exponential growth is there. And we can also calculate for a given graph. That is the open problem. For a given specific graph, for a given known graph, can we have patinate or what, or at what marking, or what kind of, or how many number of places, how many number of transition, or how many what is the arrangement of the arc or the marking, we can have this graph. Let us suppose reverse we can also see. So in this way the patinate area is very important and very even after joining my PhD, I'm doing a one project, tuberculosis project. We found we published 2 papers, and we have very interesting result. And third paper is also in communicating position we have. And thank you very much, sir. Tarkeshu sir, Professor Jessica sir, and Acharya ma'am. Thank you, ma'am. I cannot forget, ma'am, your contribution to make my life, ma'am, uh, so interesting, ma'am. And
Thank you very much.
Tarkeshu sir, I need 4 to 5 minutes in the inaugural validity session.
Okay. No
Yes,
problem.
I will
No
to
problem.
show.
I think Dr. Jessica will take care of that one.
Yes.
Yes, no problem at all.
Yeah. Yes.
So thank you, Dr. Gajendra Singh, for giving
Thank
a
you, sir.
nice lecture on petri net theory, and which was the work done with my super guide guru, Dr. Acharya and Dr. Vidi Acharya.
मेरी भी
And
गलती सर.
fourth family, I think, no? Third.
I want
Yes.
to ask you one question.
Yes, ma'am.
And do you have any comments and questions from the...
Yes, ma'am.
One question. My
Yes, ma'am.
question is, when in the last you give an example of disconnected petri net, at
Yes,
every
ma'am.
place having 1 token, 2 token, or 3 tokens,
Yes,
then
ma'am.
choice reachability tree.
Yes.
Okay. But now I want to know, is your system is alive, dead or alive? Live.
Ma'am, in this case, system will be dead. Some stage it will be automatically stopped because the old transition are sync transition. Sync transition property is that token will consume automatically. It will end.
I give you a problem. Okay.
Yes, ma'am. Yes, ma'am.
In order that your petri net is not you should not have a disconnected petri net. Okay.
Okay. Okay.
You have
Okay.
a connected petri nets. There is
Huh.
result. You must know. I'm not going to tell her. These are basically they are digraphs.
Yes. Diagram.
So what
Bipartite
is
diagram.
necessary and sufficient condition
Hmm.
for a digraph so that is when you get a reachability tree, the system is alive. It never becomes dead.
Ma'am, say again, ma'am, please. Then I can give you an answer.
The
Right.
result is already there. Okay. So
Yes,
now
ma'am.
I want to give the work. You draw a reachability tree. Okay.
Okay.
From the reachability tree, you can find out whether system is dead or alive. Okay.
Okay. Okay.
Now, what should be the property of that petri net? Basically, diagram,
Hmm.
so that
Okay.
it gives you a live. Always their system will be will be live. At least one system, one portion will not be dead.
Okay, ma'am, इसमें ये हो सकता है if we take one transition as a source transition.
No,
it
no,
is-
no. There is a condition. There is already result is there. You study. Okay. You study that result. There's a property of a diagram which will make your system will always be live.
Okay. Okay. I will see.
Another, one girl is doing PetriNet, working with me on PetriNet. She just for her knowledge. Now, what we wanted to ignore that property. Suppose that property is not there. Okay, suppose some other property is there. Can be it 0 live, 1 live, 2 live, 3 live.
Yes, classification is there, ma'am. Yes.
So
Yes. Okay.
that in that way you do the work and you have to proceed further. Chapter 5 of the Peterson's book.
हो गया मैम, वो कर लिया उसको लैंग्वेज का.
पीटरसन का बुक जहाँ पे छोड़ा था.
मैम 5 कर लिया है, 5 आगे जा रहे हैं अब उसमें.
अभी आगे जाओ, you will get lot of problems.
Yes,
okay?
ma'am.
So myself and that girl, we are going to
Yes, ma'am.
submit that paper.
Okay.
That is, see, all the system may not be live. Okay, at least one system will be there which will be live.
Yes, ma'am.
Because basically, if you see the application side, you take a mechanical engineering. Mechanical engineering, you go to the production. Okay, if some machine gets dead, your production is stopped. At least
Yes.
some part of the machine should be working so that
Always.
production is taken.
Parallelly. Yes.
So that application comes mechanically. Even you can take in civil engineering, in transportation problem and all other things.
Yes.
But that is the property of since the petri nets are bipartite digraphs. What is that property of the digraph which gives you a live system?
Okay.
Okay, try for
Yes.
that.
Yes, sir.
Thank
Yes,
you very
ma'am.
much.
Thank you, ma'am. Thank you very much. Thank you, sir. Thank you, Professor. Just asking, sir. And
Comments for other
is also and all. Thanks to all.
and other things. No.
Thanks to all.
Now I'm not working because I don't have a student who can be, you know, how do you call it, Janoon. Should have a Janoon for work.
Ma'am, grand student है आपके. You have many grand students. So,
Janoon wala
I
student
also-
चाहिए मुझे. A person who has a desire, yes, I have to do this work.
Okay, ma'am.
Is missing among the students at present.
I have one student,
I may
ma'am.
be wrong also. Professor Kiki or Professor Bhotani, Professor Jaslavsky, I may be wrong. But this is my understanding that Now we are getting the research students coming for PhD, but they don't have that junoon which we used to have. Thank you very much.
Ma'am,
Any other questions?
yes, any question?
Let us finish.
There are no questions from the participants, but if the
Okay.
panel has any more questions, there is only one question that has been asked regarding the software that Sir has used to draw his graphs. So if you can, Gajendra Sir can tell.
Yeah, there are many software. One is Patinet tool. Patinet tool that is embedded in the MATLAB. Then they can use one of
Thank
the
you,
very
sir.
good tool, MATLAB, and one is uh, one is pipe is there. One is Woped is there. One is Charlie is there. One is LOLA is there. So many softwares are available. More than 25 softwares that for the various kind of patinets. I have used the patinet only the ordinary patinet, but there are some classification of the patinet: continuous patinet, stochastic patinet, hybrid patinet, and so many various kind of patinet that we can use. Or timed patinet, one kind of patinet is there. So that is why that can be used almost every area in the patinet.
Thank you, sir.
Thank you very much.
Okay, thank you, Dr.
I,
Gajendra Singh, for giving a nice lecture.
Thank you, sir. Thank you.
Okay, now Stephanie, you can take it.
thank you, Sir Tarkeshwar, for chairing this session. I hand over to Professor Natasha.
A very good morning to the panelists and to the participants. So gives me great pleasure to introduce the chairperson for this session, Dr. Kiki Shujin. So Dr. Kiki Shujin is a professor at Universitas Indonesia. She completed her PhD in mathematics from the University of Ballarat, Australia in 2005. Since 1998 till date, she has acquired a wide array of work experience. To name a few, she has been a member of University of Academic Quality Assurance Board, member of Academic Senate, Faculty of Mathematics and Natural Sciences, and Executive Director of Quality Undergraduate Education, Project Department of Mathematics Universitas Indonesia, and Secretary of Department Mathematics Universitas Indonesia. Besides these, Dr. Kiki also has a plethora of organizational experience. She is the Vice President of the Institute for Combinatorics and its applications. She is also a reviewer of several international journals such as Discrete Mathematics, Discrete Applied Mathematics, AJC, AKCE, EJGTA. Dr. Kiki has also been an invited speaker at many conferences and workshops on the national and international front. And she has also been an invited speaker at our conference, and she has spoken on building a new graceful graph through a known one. We welcome you, Dr. Kiki. You may
Thank
take
you
over.
very much, Dr. Natasha. So it's an honor for me to introduce our next speaker, Dr. Tarkeshwar Singh. He awarded his PhD from University of Delhi in 2004, and he currently holds the position of Associate Professor in the Department of Mathematics, Birla Institute of Technology and Science, Pilani, KK Birla Goa campus. His research, he has many interests, but like the main research interest in graph labeling problems and spectra of sign graphs. He also has been awarded and recognized as young scientist by the Department of Science and Technology by Ministry of Science and Technology, Government of India. He has rich teaching and research experiences. He already completed 2 research projects in hypergraceful graph, and also studies on neighborhood magic graph. He is a life member of the Ramanujan Mathematical Society, Forum for Interdisciplinary Mathematics, and Academy of Discrete Mathematics and Application. He is like one of the founder member. He already delivered more than 40 talks in seminar and conference, workshop, and many things. Right now, he guided 3 students for Master of Philosophy degree in Bartier University, KM Bataro. He is a subject expert in Goa Public Service Commission, Government of Goa, and he already one PhD students finished with the title Studies in Graceful Labeling of Graph and its Variation, but currently he's guiding 3 PhD candidates in BITS Pilani KK Birla Goa campus. So Professor Tarkis Singh, the time is yours.
Thank you, Professor Kiki, for nice introductions. So let me share the screen by the time. Okay, let me share. Is my screen visible?
Not yet.
No, no, yes,
Yeah.
yes, it is
Yeah, already.
And this whiteboard also?
Yes. Yes.
Both are visible. Okay. So first of all, I'd like to thank Professor Kiki for giving me a nice introduction. Okay. And I also thanks to Dr. Jessica Pereira, to whom I told that why not you arrange an international conference through webinar only on the birthday of Dr. B.D. Acharya. Okay. So she was kindly agreed, and she did all the works, all the team members of Aloysius, Ada, Sanda, Natasha, Jessica, they are working hard to make this event successful. I'll just take 1 or 2 minutes about to say something about Dr. B.D. Acharya and my guide. My guide is Mukti Acharya. I'm the first student of Mukti Acharya of Delhi College of Engineering and even Faculty of Technology, Delhi University. Okay, so this topic, why I have chosen, I'll come in between, but I can tell the participants, those who are going to work or those who are working in the graph labeling problems, kindly go through that dynamic survey by Galilean. Many papers are there, many papers are not quoted there, but many students, what they are doing, they are taking the topics and just doing the trial and error method, finding some results. So that is not appreciable throughout the in the world. So kindly go through that one. Try to find out some good results and get published. Okay, this is about the participants. And when I joined Dr. Mukti Acharya as a research scholar, at that time I was not knowing about any problems. So Dr. S.M. Hegde organized 15 days workshops on graph labeling, group discussion program on graph labeling problems. I attended that one, where Dr. B.D. Acharya and other Professor Armugam, R. Balakrishnan, many, they have given many topics of research in graph labeling. And at that time, I met Dr. B.D. Acharya because my guide was staying one part of the Delhi. I was staying another part of side of the Delhi, so we are not meeting regularly. When my guide shifted the residence to the campus, then I started discussion with one. And most of the times, during the morning walks, we found a lot of problems, and we solved the problems during morning walks only with B.D. Acharya. So he's like a guru, okay? And he's always in our memory, in my heart, he's always there. And he always motivates us to do some new work and good work into that area. So this is a talk dedicated to him. And when I was working in that, so I generalized the concept of graceful graph to graceful sign graph, Scolum graceful graph to Scolum graceful sign graph, and so on. So this is another type of labeling I'm just going to discuss here. So that's why I just told that this is a talk dedicated to this one. So this is a joint work with Dr. Jessica Pereira and Dr. Taumin Wang. He visited our campus last November 2019, and we are discussing about the magic labeling of graphs and distance magic labeling of graphs and distance anti-magic labeling of graphs. And there was just some application of Scolum sequences in the magic graphs. So we started working in this one, and this is a very new topic. And what I'll do, I'll just start with the basic definition of what is the meaning of the Skolem sequence, what are the things are there. Then I'll come back to the additively Skolem graph, and we'll discuss that one. So what I'll do, I'll just start with this. So let us see the little bit theory into that one. Okay. So in 1957, the Thorolf wanted to discuss structure external triple systems in 1957. And in his paper, he just discussed that one. So what he did that one, he posed problems. Is it possible to distribute a number, okay, 1 to 2n into n pairs? Say you can consider as a AI, BI, and you can still consider that without loss of generality, BI is greater than AI, such that if you take the difference, BI minus AI, you are going to get I, where I varies from 1 to n. Okay, this is a question posed by him, and he solved that also. He solved that question also. Because if you take a small example here, so it take the small example, suppose we have a set n is equal to 4. Let us say n is equal to 4 here. So if you take the set, so we have a 1, 2, 3, 4, 5, 6, 7, 8. These are the numbers are there, 1 to 2n. And what I need to find out 4 pairs. 4 pairs, AI, BI. So one pair is like this. So you can say that one pair is like this one. So I take here 1, 2. This is one of the. Then I can take 5, 7. Then I take here 3, 6. And then I take here 4, 8. Okay. So this is a possible pairs. We are going to get that one. If you see, the difference of this is 1, difference of this is 2, difference of this is 3, and difference of this is 4. So we are going to get all the such differences here. So he calls, if such pair exists, then he calls that this is a 1 plus 1 system, because it's starting from 1 and increased by 1. So that is a 1 plus 1 system. He proved that. And he said that one such a system will exist when n is congruent to 0 or 1 mod 4. Okay, it's very simple to get this necessary condition. Okay, because if you take that the difference is BI and minus AI, and if you sum it, okay, so where I varies from 1 to n, if you sum, you are going to get here n to n plus 1 by 2. And if you take all the vertex labels, if you sum all the vertex labels of BI plus summation AI, if you take, this will be 2n into 2n plus 1 by 2. Okay, and if you simplify, you will be able to get this condition. And he proved that this is necessary and sufficient conditions. So he proved that one. Okay, this is the idea behind that one. Now, why it is called Skolem sequence? Let us see here. So as you see, the positions, if you consider these are the 8 positions, say C1, C2, C3, these are the place values, C4, C5, C6, C7, these are the place values if you are going to give. So then you can see 1 and 1 will appear because of the difference of 1 and 2. Then 3 and 6, so 3 will be appearing here, and 4 will be appearing here, and 2 will be appearing here. So this sequence is known as a Skolem sequence in the literature. In the number theory, this is known as a Skolem sequence. So very simple things are there. Just if you see, if you take any number, so for example, I take 3. If 3 appears here, then next 3 appears at the plus 3 positions. So C3 plus 3, that is C6 position. You can see that. That is the beauty of this Skolem sequence. The next 3 will appear here. So this is about the literature, and many results have been proved that one. Okay. So this is a definition which I was just discussing about that one. So this is a very simple. Now, the same concept was introduced, converted into the graph labeling problem by Sinmin Lee and SCC in 1991. So what they have done, say if you see the copies of K2, so if I take 4 copies of K2 here, so this is a 4 copies of K2, and if you label the vertices as AI, BI, and you label as 1, this is 2, this is 5, and 7, 3, 6, and 4, 8, you can see if you take the difference as edge labels, then you are going to get 1, 2, 3, and 4. So this is a way he defined the Scullum graceful graphs in the literature of in the graph leveling problems. He brings that notion to this one. Now, and he proved many results. So what is the definition of a Scullum graceful graph? It's very simple here. It is a bijection. You define a bijection from 1 to the number of vertices, and you get all the edge levels from 1 to a number of edges in the graph, which is obtained by this method. So here we are taking the difference f of u minus f of b whenever there is an edge in the graph. So this is also bijection. So he said that this is a, if that condition f such f exists, then that f is known as Scullum graceful leveling, and the graph which admits such leveling we call as a Scullum graceful graph. Now, those who are working, they are knowing that one. If the graph is graceful, then q will be always greater than or equal to p minus 1. And from this definition, one can easily see that if the graph is Scullum graceful, then it is q is less than or equal to p minus 1. So when I was working in the for the PhD thesis, then my doctor, if I just used to say that one, Acharya is graceful if and only if Mukti Acharya is Scullum graceful. This is the why I have chosen this topic, because I used to say that if BD Acharya is graceful if and only if Mukti Acharya is Scullum graceful. So that is a theorem I used to say, and I proved something, many results in that area. So that's why this is a reason I have chosen this topic. Now in 1961, the O'Caffey, he's also extended the notion of Scullum sequences, and he proved that since in the Scullum sequence will exist when n is congruent to 0 or 1 mod 4, then he proved that one, if k is 0 or 2 or 3 mod 4, then such system will exist. Only thing is here, the 2k terms will be not there in the set. So their set is, there are the set 1 to 2n, but here what he did that one, he has started from 1 to 2k minus 1, then 2k plus 1, one increment he has given, and the number 2k was absent. So he is able to find out such a systems and prove that in 1961 that such a system will give, and this system is known as a hooked Scullum sequence. Okay. Now the definition of hooked Scullum sequence is like this, same way. So what I'm just going to consider, I'm just going to consider the set here. If you see, the set of numbers are 1 to 2, 1 to 3 up to 2k minus 1, then 2k plus 1. From this set, we have to consider the order pair ai and bi in such a way that the differences, absolute differences of this will start is equal to, so I just take here absolute difference, ai, bi is equal to I, where I varies from 1 to n, 1 to k. Okay, so now you can see, I just give you one example, simple example I can give you here. So for example, then you'll be able to understand that sequence, hooked Scullum sequence here. So for example, if I take n k equal to 3, so we have a number 1, 2, 3, 4, 5, then 6, I'm just going to skip here, then I'll put here 7. Now this is a set we have, and now from this set, I'm just going to find out 3 pairs, ai, bi. So what I'll do here, I'll just try to consider the pairs like 1, 2, then I'll consider as a 5, 4, 7 and 3, 5. Okay, 3, 5 and 4, 7. Now you can see here easily, this difference is 1, this difference is 2, this difference is 3. So we are going to get all the numbers 1 to 3. And when you are going to place the position, so see one appears at one position, then second one appears at the second position, then 2 appears at the third position, then 2 will appear at the fifth positions here. So I'll just say 1, 2, 3. Then here I'll just put here 3. Then this is 2. And then 3 will appear at the 7th position. And this position is unfilled because this is the 6th position. 1, 2, 3, 4, 5, and 6. This position is fixed, not there because of the number 6 is not there. So they put the star. And that's why it is known as hooked Scullum sequence. So this is known as hooked Scullum sequence. Okay, Scullum sequence, this is known as hooked Scullum sequence. Now many idea then Simpson also proved that were perfect sequence about that one, and he gave a definition about the perfect sequence. So not only the sequence d plus 1, d plus m minus 1, which are the m conjugative positive integer, not starting from 1. It can start from any number d, okay, which is going to be selected. The order pairs will be selected from 1 to 2m numbers only in the same manner. Then Simpsons called this is a perfect sequence. Now, motivated from this one, we have defined the KD hooked Coulomb sequence and KD Coulomb sequences. Okay, using the graph theoretic terminology, graph leveling. So what we have defined that one, myself, Jessica, and Professor Armugam, we have defined that one. So if we have a graph PQ, we say that it is KD hooked Coulomb graceful graph if the vertices are labeled from 1 to p minus 1 and p plus 1. And if the edge labels are considered as an absolute difference of the end vertex labels, then all the edge labels will be k plus d, k plus 2d, and so on. And we got many results like that one only. Okay? And there are some necessary and sufficient conditions we are able to get that one. So this is a one things also we are going to get this part. Q is always less than or equal to p minus 1. That is immediately we can say. If k and d is equal to 1, that is the usual Coulomb, hooked Coulomb and Coulomb graceful leveling of the graph. We are going to get that one. And we generated many results on that one. These are some known results. Let us forget about this one. Okay. These are some known results about the KD hooked Coulomb graceful graphs and KD Coulomb graceful graphs. Okay. Now let us come to this part. So what we have taken, in short, I have taken as ASG means additively Coulomb graph, graceful graph. So what we have discussed here, since we are trying to find out some results in the distance magic and distance anti-magic graph, and we found that Coulomb sequence are also useful to generate such. So can we define something like that instead of a difference? So if we label the vertices from 1 to p, okay, and if you take the edge labels like a sum of the end vertex labels here, then if all the edges are starting from k, k plus d, k plus 2d up to k plus q minus d, where q is nothing but the number of edges in the graph and p is the number of vertices in the graph, then such leveling we call as a additively Coulomb graceful leveling. Okay, such leveling we call as a additively Coulomb graceful leveling, and the graph which admits we call as a additively Coulomb graceful graph. Now from this, this is a very simple one to get this lemma. Proof of this lemma is very simple. I just illustrate here only. Okay, I have some space. How much time do I have, madam? I think I have some time. So let us start with this one. So as I told you that the labels are from, if you take n copies of K2, so we have how many labels are there? 1 to 2m. Okay, these are the set of numbers which are available to us. Okay, what I am going to get? I am going to get an order pair AI, BI from this one way. So each AI, BI I am going to select from this set. So suppose this is my set S, and from that, what I do? I just take the sum, because edge labels are obtained by. So if there is an edge like UV is an edge, so induced edge labels is defined in this manner. So f of u plus
Excuse
f.
me, sir.
Yes.
So you have 10 more minutes.
Okay, no problem. So if you are just going to take this way, then easily you can see if you just sum the labels here. Okay, so in the right hand side, I'm just going to get the edge labels as starting from k, then k plus 1, and so on, plus and so on, k plus q minus 1 into d. So n is the nothing but q here. I just take here k plus n minus 1 into d. That is a d is 1 here. Okay, d is 1 here. This is a minus 1. And left hand side is nothing but the sum of all these labels. And if you simplify further, you are going to get this conclusion actually. If you simplify, this is k times n plus how much I think n into n minus 1 by 2. If you simplify, you are going to get this one. So this is a one conditions. necessary condition we can use from this simple number theoretic properties, and then we'll prove that one. So we have proved this one, that is if and only if case. Okay. Now next, what we have done, instead of 2n of the set of integers we have taken from 1 to 2n plus 1, we have started that, suppose in some cases, if you see here, this must be an integer, this k must be an integer here. Okay, so when k must be an integer, so n must be 1 mod 2. So what is about the when n is an even number? So what can we say about that one? So we cannot get a additively Coulomb graceful leveling for that one. So we just started with the, okay, can you think about the hooked version of this one? So here L is the number. If you remember, in the cafe results, we have started the numbers from 1 to p minus 1, and then p was not considered, and then p plus 1. So instead of that last number, 2n, we can take any arbitrary number L. So I'm just going to take the set here. The vertex will be labeled from what of the graph from this one 1 to L minus 1. Then you can see here L is not there. This number L is not there. Then P minus 1, P plus 1. So not necessary that this number will be absent. You can take any arbitrary number which are not there in this, and then you label the vertices of the graph and take the edge-induced label as a sum of these two vertex label of the n vertices. And then if you are able to get the number edge labels as k, k plus d, k plus 2d up to k plus k minus 1, q minus 1 into d, then we can say that this is a additively hooked Coulomb leveling, and the graph which admits such leveling, we say that it is a additively hooked Coulomb graceful graph. And these results are, there are some results we are able, same way we are just going to get here. So as you know that one, we have a set of numbers. So 1, 2, and then we are just going to take L minus 1, then L plus 1. So L is not considered here, and all the labels are 2n. We are just going to consider here 2n and 2n plus 1. Okay, 2n and, sorry. So I just take this one, 2n plus 1 also we can take here. And then we can find out that one. So easily we can say that all the ordered pair sum, if you are just going to take in the same manner, you are going to get this condition. And this must be an integer. Okay, this must be an integer. This is a necessary condition. We are able to obtain that one. Now, these are the following results I'm just going to discuss here. So this is a one lemma. If the graph is 2s, means s is even any number, 2s copies of K2, then it is LK1, additively hooked Coulomb graceful graph, when L is either s plus 1 or 3s plus 1. Okay. Similarly, if it is there, then either it will be s plus 1 and 3s plus 1. We are able to find out the sufficient condition for that one. And then we prove the following results, that if and only if case. We prove the following conditions for the if and only if case. Now let us take one small example, and then I just try, okay, I have some time. Okay. Now let us take a small example here. When I'm just going to consider this, let us say first, when L is s plus 1, L is equal to s plus 1, this case I'm just going to consider. And then I just consider here when L is ps plus 1. With this example, I just give you the idea of the proof about this one. Okay. So I just consider s as a, let us take s as a 3 here. Okay. So now what I'm just going to get here, so 3 plus 1, 4. So I'm going to get here the 4, comma, 12. Okay, k is 12 here because starting from k, and then I'm going to increase by 1. Okay, this is the case I'm just going to consider that one. And additively hooked Coulomb graph, I'm just going to consider that one. So k copies. So I just take here s is equal to 3 here. So we have a, I just take a label like this one. Let us say here I take 1 copies, 2 copies, 3 copies, then 3 copies, 4 copies, 5 copies, and 6 copies, because 2s copies of K2. I'm just going to consider. Now label the vertices in this manner. So what are the labels are there from? We have labels from 1 to up to 30. Okay, so K 12, just see that one. There are 12 vertices. So we are going to start from that one, and then this number will be absent in that. Okay, so I just label the vertices like this: 1, 2. Then we have 5 and 8. Then we have 2 and 12. Sorry, this is 11. Okay. This I'll take as a 11. Okay. So I'll take here 11. Then this is 12. Then we have a 6 and 9. Then 3 and 13. And 7 and 10. So now if you see the age labels here, okay, age labels, this is starting from 12, some 8, then 13, then 14, then 15, 16, 17. So these are the all age labels. We are going to start from 12, and then increment is D is 1 here. And you can see in the vertex label, this 4 is missing here. Now when you are just going to place that numbers in the positions here. So what are the positions are there? I'm just going to take here. There are 13 positions are there. So we start from C1, C2, C3, C4, C5, C6, C7, C8, C9, C10, C11, C12, and C13. Now I see that one. Where 12 appears here. So 12 is a 1 plus 11. So first 12 will come here. 12 will come here. Then where the 12 will come again? At the 11th positions. So this is a 12 now. Now similarly, 16 will come at the 13th position as well as at the 3rd position. So 16 numbers will appear here. Now at 5th position, 13 will come. So just and 8th position also 13 will come. Then at the 2nd position, 14 will come. Then 12th position also 14 will come. Okay, so this is a 14. Now, if you see this one, 16. 16 we have done already. 15. Let us take 15. The 6th position, 15 will come. And then at the 9th position, also 15 will come. 17 will come here at the 7th positions, and 10th position, it will come at the 17th. Now, these positions are still not filled. So, this is why this is called as a hooked. And similar property you can see. What are the fashions are there? If one numbers appear at the ith place in the column sequence, then second numbers will appear at the I plus 1th place under that one. So this in the same manner we can relate this one, that if the first number appears 12th as here, then where the second numbers will appear, immediately you can get that one. This is another example I am just going to get when S is equal to 3n plus 1, L is equal to 3n plus 1. So when we take S is equal to 3 only, so let us say here S is equal to 3, so L is now 10. Okay, so that number 10 will be missing here. So I'll just start that this number is hooked, and I'll start from 12 only, not 12. So 10 plus 1, 11. I'll take 11, and then I'll increase this one. So this is a additively hooked is column graph. I'm just going to find out, sir. So there are 6 copies. S is equal to 3. So 6 copies of K2. I'll just take that one. And again, if it starts from that one, I just label. This is a 3, 4, and 5. I just label the vertices. Let me take 1 minute time to label the vertices. 9, then 4, 8, 6, 7, and 1, 13. Okay, and 3, 12, and 5, 11. Now you can see easily here. You can easily see here, it is starting from 11 and growing up to 1, 12, 13, 14, 15, and 16. Now, in this case, you can see the number 10 is absent, vertex level. It is absent from the vertex level. So again, you can get the same sequence. If 1 appears at 14 will appear at the 1 place, then another 14 will appear at the 13th place. So 13th place, 14 you can write. Then 11 appears at the 12th place, 2nd place, then that will appear at the 9th place here. Like that, you can easily find out that one. See, 15 appears at the third place, so you can write that sequence 15, and then here we are going to write here 15. Like that, we are going to get all the such sequences here. So this is a similar sequence, and we are going to get that one. So in this talk, what we are going to do is the following. Okay, all the results which we have proved using the graph leveling of the graph, and the weight of the edge is calculated as the sum of the n vertex, and we are going to get a new results which are also a somewhat look like a Skolem sequence or hooked Skolem sequence, and it has many applications in the anti-magic and distance anti-magic graphs. And just before the conference, when I invited Professor Wang to give a talk, then he was just saying that he will not able to give a talk, but you can present this talk as a joint work. And he has suggested that this will be applied to label the hypergraph. So we are working on the labeling of hypergraph using this additively Skolem graceful sequence and additively hooked Skolem sequence for the hypergraphs, and going to get some new results. Okay, so with this, these are some results we are able to find out. Again, if and only case we are able to do with the disconnected 2s copies of K2, and many other results we are able to find. We have established that one. So this is another results we have discussed, that when n is equal to 2s minus 1, then also it is going to be additively hooked Skolem graceful graph, and many more. So these are some results we are just going to discuss that one. Okay, so this is a conclusion. We are able to find out some necessary and sufficient conditions. Okay, in general for the graph, as well as we have proved that necessary and sufficient condition for k copies of K2, n copies of K2, which is additively Skolem graceful graph, and which are additively hooked Skolem graceful graph. So this is the one we are just going to, I have presented here. Any questions or queries and suggestions, you are most welcome. These are the references I am taking. So one references was missed out, that is by Siemens, perfect Skolem sequence. Okay, these are the papers we have already proved that one about the KD Skolem graceful graph and KD hooked Skolem graceful graph. I think I'm in time.
Thank you very much for a very interesting talk. So Professor Takesur, sorry, Tarkiswar Singh is giving us like a very nice way how to show the Skolem sequence, and like give the motivation to introduce a new graph labeling. Any question? Maybe I cannot see the chat. Natasha?
Right now, there is no question. There was one question, but it is not phrased properly, so I couldn't really figure out what that question is. I've asked them to rephrase it, but nothing has come yet.
Okay.
So maybe from the panelists, if
okay,
there is a question.
Understand?
Any question?
I have one request for Tarkeshwar.
Yes,
please.
जो तुम्हारे papers which has been published on Skolem, this paper, I want those papers.
Okay.
You send me, okay?
Okay.
I will think further and tell you.
Yes. We are trying to bring into the sign graph only.
I was thinking that only.
No, the paper is there. I already discussed with you, that paper hooked Skolem graceful sign graph is there. Okay, so that I have to send, and myself, Jessica, and you can do that one.
You send me the papers, I will read and think further, okay?
Yes, madam.
Okay, no problem.
So that's great. So there will be a new papers produced maybe in the near future.
And I'll also invite Professor Kiki, if you have some idea about a new additively one, so we can have some collaborative work.
Yeah, thank you very much. But
this is very new topic.
I still have to learn about what is how to do the column graceful, and the other one is Hooke's column graceful. So
yes, yes. We can have a Google Meet and we can discuss.
Yeah. Okay, thank you.
We can find out some
Yeah,
common
so
time.
I think the session is ended. So I give the session back to Natasha.
Yes,
Or-
thank you so much.
Yeah.
Thank you so much, ma'am, for chairing the session. And also thank you so much, Professor Tarkeshwar, for giving us a talk on Hooke's column graphs. And now over to Stephanie.
Thank you, Natasha. We will move on to the next session. Our chair for this session is Professor Natasha D'Souza E. Jacques. She attained a master's degree in mathematics from Bangalore University in the year 2004. She then pursued MPhil in mathematics and graph theory from Bharatiya University under the guidance of Dr. Tarkeshwar Singh, BITS Pilani, Goa campus. She is an assistant professor at Don Bosco College of Engineering, Goa. She's currently pursuing her PhD through BITS Pilani, Goa under the guidance of Dr. Tarkeshwar Singh himself. Her research interests include domination in graphs and graph labeling. Natasha, I welcome you once again, and I request you to take over.
Thank you, Stephanie. I now introduce the speaker for the next session, Professor Aloysius Gudino, who will be talking on magic labeling. Professor Aloysius Gudino is currently pursuing his PhD in mathematics from BITS Pilani KK Birla Goa campus. He has been awarded the Shri Yashwant GK Scholarship for obtaining first rank at BSc examination conducted by Goa University in 2011, second rank at MSc degrees examination conducted by Goa University in 2013. He has also been awarded Junior Research Fellowship by National Board for Higher Mathematics and has qualified for UGC Junior Research Fellowship in 2017 and was selected for Elite Study in Taiwan Scholarship Program in February 2018. He visited TIFR Mumbai campus as a visiting scholar to work in September 2018 to collaborate with Professor Amitava Bhattacharya on graph theory related problems. He also visited Tungai University campus, Taiwan, during 2018, an internship under the Elite Study in Taiwan Scholarship Program. He has 8 publications to his name. He is currently the assistant professor at Rosary College of Commerce and Arts, Naveli, Goa. Aloysius, I hand over the mic to you. You can take over the session. Aloysius?
I think, Natasha, you have to wait for a moment. He has some problems, technical problems.
Okay, we will wait.
Okay, just wait for a moment.
Yes, sir. Yes, sir.
It is raining here. Okay, heavily raining. No, outside it is heavily raining. Maybe network issues. Just
all right, sir. Yes, sir. Yes, sir.
Professor Armugam is also connected with us. Professor Jaslaski is still there. It is raining, heavily raining.
Hello. Hello.
Yes, sir. Yes, sir. It is heavily raining in Goa. So maybe that create a problem for network.
Professor Jaslaski is not getting sleep.
Yes, yes. I think he is in, his mind is involved in many research problems.
Yeah.
And the last day he will just, I think Professor Armugam and Jaslaski will float so many problems in the concluding session.
No, I don't think so. I think I'm going to fall asleep.
Okay.
Since we're waiting, Tarkeshwar, I have a question about, or a suggestion, a thought about your topic. You were talking about LK1 hooked skull and graceful graphs.
Yes, sir. Yes, sir.
And so there are, and you were talking about that particular graph, 2S K2.
Yes.
Okay, and then L can be exactly either S plus 1 or 3S plus 1.
Yes, sir.
Okay, there's a symmetry there that
Yes.
S plus 1 and 3S plus 1 are symmetric. So in
Symmetric.
other words, basically the same solution applies for the S plus 1 and the 3S plus 1 by reversing the sequence.
Same solution. I didn't look into that way, sir.
I'll
Because
send you an email.
Because the necessary condition says that k must be an integer where k is in the form of 3n square plus 7n plus 2 minus 2l upon 2n. So that must be an integer.
That's a separate question.
Yes.
That's not what I was thinking about. I'll write you an email.
Okay, sir.
Then
So
I can explain
there is
better.
symmetry. Okay.
And thank you for explaining skull and graceful graphs and hooked skull and graceful graphs. I never understood them before.
Yes. Sorry.
Good explanation. No, you did a good job.
Okay.
Thank you.
Thank you very much. So I'll just look into that one. You just send the mail, sir. How
I
we
will.
get the same thing, huh? Okay.
I'll send it later.
Yes. Sir. Yeah. But
Yes, Aloysius is trying to connect, so maybe another 2 or 3 minutes.
Okay. Because of the rain, no, I think disturbed. That's why I'm in the office. I'm not at home.
Yeah, so I just called him up. He said he's just there, 2 minutes. Yeah.
Okay. So Professor Jaslavsky is still there?
After this talk, you will have a lunch break?
Yes, madam. After that, Deepa Sinha is going to give a talk.
Okay, then lunch break, eh?
No. First lunch break. After Aloysius's talk is lunch break. Then Professor Deepa Sinha will give a talk at 2 o'clock.
Okay.
Yeah, so we come
And
back.
after that, Purnima Gupta might be ready because she was having some fever and other throat infection. So she will give a talk.
Okay.
Yeah, Jessica, I was about to ask because in the
Yes.
schedule it said Purnima Gupta will speak now, right?
Yes, she requested us to shift her time to the last lecture because she may feel better till then.
Okay,
So that was the reason why Aloysius was shifted here.
I see. Okay.
Now, this is a season where people get affected by viral. Then Delhi side, dengue, chikungunya.
The dengue and chikungunya is not there. COVID is more serious.
COVID is more serious. Okay.
Not serious, they have made us more active. More conscious about our health, about our going outside.
Yes.
Always we will say, according to me, everybody is a carrier.
Yes.
Everybody is a carrier, okay? Whether we give or we get from otherwise does not matter.
If everybody is going to think like that, then there will be no problem with the COVID.
Yes. But still we take now health has become more important than money.
Yes. Now this COVID taught us. COVID-19 taught us that health is most important than the money.
Yes. Then the parties, going to hotels. Now everybody is cooking in the house.
Yes.
Okay.
And also it taught that false relations. So many people are having some friendship relations, but knowing relations, but they are not in the.
We also learned to cook new things.
Yes, I'm telling now we are cooking gulab jamun, rasgulle, all things which used to go outside and eat. We do it in the house. But I will put in other words. No, love birds are not there.
Yes, definitely.
But nowadays I find actual birds, kabutar.
No, peacocks. Peacocks are there in my campus.
A lot of pigeons come on the street.
Yeah.
Another thing.
Small birds.
No, peasants in my lane, they believe if you put bajra, na, 50-60 aate hain. Which
No,
one?
many beautiful words are coming to my campus.
Yes.
Even peacocks are coming, running here and there.
Yes, yes.
And all the dogs of the campus are surprised. Where are the human beings? They are not. They are confused whether that dog catching vehicles have caught them.
Okay, I think we have Aloysius with us. Yeah.
Yes, we have Aloysius. Aloysius, are you ready?
Yeah, I'm there.
Yes,
please
I've
share
introduced
screen.
you.
We are waiting, eagerly waiting.
You can share your screen.
Okay. Yeah, give me 1 second.
Madam, he is your grandson.
Who?
Hello,
Yeah. Yes, a grandson.
Jessica is granddaughter. Natasha is also granddaughter
Yeah.
from my side.
I am honored to be one.
Yeah. I know you since a long time, 2013. Before that we met, na? Before
Yes, yeah.
Now, yes.
Yeah, can you see my screen?
Yes, we can see your screen.
Okay.
Go ahead.
Should I start?
Yes, you can start. You can start.
Okay, so in this talk, I will just discuss about distance magic labeling of graphs. So I will begin with, some motivation. So suppose I take the graph K5 minus maximal matching. So I'm going to assign labels from 1 to 5. Since we have 5 vertices, I will assign numbers from 1 to 5. So in this case, I can assign the numbers, for example, like this. So the vertices receive the numbers 1 through 5. If I consider any vertex, for example, this vertex, I can look at its neighbors. The neighbors of 5 are 1, 2, 4, 3. If you add these numbers, they sum up to 10. If you consider any other vertex, for example, 2 is adjacent to 5, 1, 4. If you add these numbers up, again, it adds up to 10. So the neighborhood sum of every vertex is 10. This graph is said to be a distance magic graph. So distance magic labeling of a graph of order n is a bijection from the vertex set to the numbers 1 to n, such that the neighborhood sum for every vertex is C, which is constant for every vertex in the graph. So where NV is the open neighborhood of the graph, such a labeling exists, then the graph is said to be a distance magic graph. So these are some examples of distance magic graphs. I have a table over here. So if you look at order 1, there are no magic graphs of order 1, but there's only one graph of order 1. For order 3, there's only one magic graph, which is P3. For order 4, the only magic graph is C4. Order 5, the only magic graph is K5 minus maximal matching. For order 6, the only magic graph is K6 minus maximal matching. For order 7, it is K7 minus M and P3 union C4. And order 8, similarly, we have 4 magic graphs. So there are very few graphs which are distance magic. So we look at circulant graphs in this talk. So let's just have an example. Suppose we have 8 people sitting on a circle. We can assign numbers from 1 to 8 to these people. For example, I can assign numbers in this way. So each person gets a number, a unique number between 1 to 8. So every person, he will ask the two people on his left and 2 people on their right what their numbers are. For example, if you look at 1, his 2 adjacent neighbors are 2 and 3, and on the right-hand side, 8 and 7. So if he adds up 2 plus 3 plus 8 plus 7, his sum comes to 20. Okay, similarly, another person, for example, person with the number 5, can ask the people on his right what the numbers are, and people on his left what their numbers are. So he's going to get the sum 4 plus 3 plus 7 plus 6 is also 20. So if every person gets the same number, then it's called a distance magic circulant graph. For example, so this is the graph that we're looking at. We're looking at the graph C8 power 2. It's the power of a cycle. So this was proved by some researchers. They have proved that if R is odd, then the graph C n power R, distance magic if and only if R, 2R into R plus 1 is congruent to 0 mod n, and n is greater than or equal to 2R plus 2, and n upon GCD of n into R plus 1 is congruent to 0 mod 2. This problem was open for R is even. So we solved this problem for R equal to even, and we got the solution that if A is equal to GCD n R is odd, so this problem was solved for, I think I wrote the wrong result. So we have proved for even also. I didn't include the result over here. But this can be extended to normal circulant graphs. So a graph G said to be circulant if and only if its automorphism group contains a cycle of length Vg. For example, we can look at this graph. So every vertex in this graph is joined to the second vertex on the, so you can imagine there's a cycle on this graph. So every vertex is joined to the second vertex and the fourth vertex on this imaginary cycle. So this graph is called C12 to 4. Every vertex is joined to the second vertex and the fourth vertex on a cycle. So we have shown that for circulant graph Ci n R1 up to Rk, where these Ri's are in an arithmetic progression, where D is the common difference. In this case, a circulant graph with distance magic if and only if we have two conditions. The first one is when it is even, when n comma kd is even. The graph with distance magic if and only if rho into this is equal to 0 mod n, where tau is the order of rho in zkd. And when GCD n comma kd is odd, then the graph Ci n R1 up to Rk, distance magic if and only if n is even and rho into tau is congruent to n by 2 mod n. So here's an example. For example, we have Ci circulant graph on order 12 and 2 4s. Every vertex is joined to second vertex and fourth vertex on the cycle. And this is the magic labeling of the graph, and the magic constant is 26. In the example, we have Ci 72. So there's 72 vertices. Every vertex is joined to the third vertex, the sixth vertex, and the ninth vertex on the cycle. The magic constant here for this labeling is 219. The way we label this graph is, it's a very standard technique. We come up with these sequences. These sequences are very common. For example, we use them in magic rectangles and so on. So you write down the sequences and we label the graph with the help of the sequences. So for example, the first sequence would be, we'll label these vertices, then you just move to the right. Next sequence, label the next vertices on the right. Keep moving on the right and so on. So we label every vertex in the graph. Let's come to nearly distance magic graphs. So in this case, what we have done is instead of having only one magic constant, we allow for two magic constants, but the magic constants can be separated only by one. So they have to be consecutive numbers. So let G be graph of order n. A bijection from the vertex set to 1 to n is called a near distance magic labeling of G. If there exists constants k1, k2, where the difference between them is less than or equal to 1, such that the sum, again the neighborhood sum, has to be either k1 or k2. So we are allowing two magic constants, but they can be consecutive numbers only. The magic constants k1, k2 are called the constants k1, k2 are called the magic constants of the graph. And the graph admits such a labeling is called near distance magic graph. So for example, we have the graph K433. This graph is not distance magic because magic constant turns out to be a fraction. We can prove this by using the formula for the magic constant. This is going to be a fraction. There is no way to get a magic labeling for K433. So we use a near distance magic labeling. So here's an example. So we have two magic constants here. One is 36, one is 37. So they're separated by 1. It's a near distance magic labeling of the graph. So we've also obtained the formula for the magic constant. So this first formula for the normal magic labeling was obtained by Arumugam and Slater. It shows that if G is a distance magic graph, then the magic constant is given by n into n plus 1 by 2 times the fraction total domination number of the graph. Fraction domination number is given by this formula. It's a linear programming problem where the minimum is over 1 transpose into y, where 1 is a vector of all ones subject to a into y.
LSA,
yeah.
The Arumugam and Slater work separately and given the formula.
Yeah, they work separately. Yeah, they did it separately in group together, but they did it separately.
There is a separate research work. Yeah.
So this is the linear programming problem to obtain the fraction total domination number It's a minimum of all, this is the summation of all yi's, where the summation is taken, so subject to the condition a into y is greater than or equal to 1, where a is the adjacency matrix of the graph. So for example, for this graph, I can't use my pen. So for this graph, the factorial domination number comes out to be 3 by 2. So if you use in the formula, the magic constant turns out to be 10, which is exactly what we get in this case. So what we have shown is that if you allow for two magic constants, if you allow the graph to have two constants, k1 and k2, then the constants k1 and k2 given by this formula, the formula for k will be is the floor function of n into n plus 1 by 2n fraction domination number of g. So if you allow for two constants, then the magic constant k will be a floor function of the usual magic formula. So we also proved that the graph n copies of C4 union P2 is linear distance magic with the magic constant 4n plus 2 and 4n plus 1. And we've also shown, for example, this is the labeling of the graph. So we have 4 copies of C4 and 1 copy of P2. Also shown that the graph NC4 union K23 linear distance magic with magic constant 4 into n plus 2 and 4 into n plus 1 plus 3. So based on this, so this is an example. So based on this, we then show that all natural numbers except 4 appear as magic constants of some linear distance magic graph. So all numbers appear as a magic constant of some magic graph. So I'll end with a theorem which is proved by B.D. Acharya. So he proved an embedding theorem that says that every graph can be embedded as a distance magic graph. So a graph edge can be embedded in a graph G if there exists an induced subgraph G prime of G such that G prime is isomorphic to H. So we put every graph can be embedded in a distance magic graph, and based on that, we can show that there are no forbidden subgraph characterizations for distance magic graphs. So I think I'll end with that. Yeah.
Yes, thank you, Aloysius. So would there be any questions from the panelists?
Who gave this the name, distance magic?
This was given by, there's a thesis in 1991, in that this name appeared. It was in 1991.
It seems
different name were there. And when Professor Armugam organized one workshop, from there onwards, people are concerned that one. Since Mirka Miller has given a name as a one vertex distance magic graph, then neighborhood magic graph was given by B.D. Acharya and myself, and then Sigma labeling graph was given by some other group. So now Armugam and Deliver Francek and other group joined together and said that no, let us have a distance magic graph only level. Now, then onwards, it was a distance magic graph.
It seems to me that the name neighborhood magic graph is the correct description of it, and distance magic is very misleading. I am definitely for neighborhood magic.
It is a neighborhood magic, but we have already done with the any d distance magic. So you can take any d distance neighborhood of the vertex.
Well, see, it is not about distance. Distance is not relevant to this concept. So it's not a good name.
Okay.
Now, if I were to think of a distance magic graph, I would think of something like that when you look at a vertex, you add up all the vertices with the number of the vertex multiplied by the distance from the vertex you're looking at. So if you're looking at a vertex U, then you take all of the vertices labels that are the neighbors with multiplier 1 and the vertices that are second neighbors with multiplier 2 and so on. That sounds like distance magic. That's a completely different concept.
Oh yeah,
So,
I think this will be a new area. We can work about that one. So distance vertices which are just a neighborhood, we can multiply by 1, and then the distance 2 we multiply by 2 and add up. I think that can be consider as a new concept and work on that one. Nobody
Well,
has done such kind of this.
you're very welcome to follow that idea if you want to.
Yes, yes, yes.
But it should be called distance magic and the other one should not be. Okay, anyway, I leave that to you. But if you like the idea, please go ahead.
Yes, 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 yes. So
there's another question from the participants. So I think the question is not very clear, but I will still read it. It says, when is a nearly distance magic graph a distance magic graph? So I think they probably mean, is it possible for us to embed a distance magic labeling into a nearly distance magic graph or
not
something like that?
distance.
Yeah, it's possible. It's possible to embed, of course. Yeah.
Yes.
But
Okay.
no,
I
it's
would.
a wrong.
I'm sorry. Go ahead.
No, no. Tell
Yeah. So not every nearly magic graph is magic. There are some conditions. Yeah, but not every nearly magic graph is going to be magic.
Now the question is, can you embed a nearly distance magic graph into magic?
Now, that's a different question. I interpret the question differently.
Yes,
I
sir.
interpret the question as saying, when is a nearly distance magic graph actually a magic graph? A distance magic. Is that a reasonable interpretation of the question?
Yeah. So yeah, every nearly magic graph. Yeah.
In other words, I would interpret it as saying, is it true that when the fraction that you compute is an integer, that this nearly distance magic graph is magic, is actually distance magic?
That's not always true.
So that's okay. So that's interesting. Thank you.
All right. Any more questions? Would there be any more questions? Okay. Since we don't have any more questions, I would like to thank the speaker. Thank you, Aloysius. It was a good talk. And I would over to Stephanie.
I thank Professor Natasha for chairing the session and also to Professor Aloysius for his session. Thank you. Professor Jessica, can we break for lunch now?
Yes, we can break for lunch and we get back at 2 for the next session.
So, panel and participants, please note that we are breaking for lunch and we will be back at 2 o'clock.
Can I ask one question?
Yes, sir.
Yes.
Yes, sir.
It's about the schedule. The schedule has been changing.
Yes.
So
Yes. The next talk is Professor Deepa Sinha at 2 o'clock.
right.
And after Deepa Sinha, 2:50, Professor Purnima Gupta will be giving her talk.
Oh, thank you. Okay, that was my question. Thank you very much.
Yeah, thank you.
Okay, great.
So, Professor Jaslavsky. So,
Yes.
This is a question you want to pose, that when a nearly distance magic graph is distance magic.
Yes.
Yes. Okay. So this is not okay. We'll try to see this one. And another concept which we have given is if suppose we are going to take a graph where I think I can discuss with sharing the screen. Can I share with the permission of Natasha?
Yes, absolutely, sir.
Yes, sir.
Yes, absolutely.
Let me share that screen. I'll just take the board. Well, so I think Professor Jaslavsky was giving a new idea about that one. So if we have a graph, you take a vertex and see the adjacent neighborhood of vertices which are at distance 1, then at distance 2, and like that. And when we label this one, so I'm just going to, sir, is it visible, this screen?
The screen is visible, sir.
Okay.
I see a screen, but I don't see a graph.
I'll just draw that one, sir. Just 1 minute. Within a second, I'll just do that, sir.
You have a blackboard.
Yes.
It says welcome. Thank you. Yes.
So this is, I think you are going to say that, no, sir. So this is my graph G. And if we take a vertex here, and I just take a vertices which are distance 1, level 1, level 2, like that.
Yes.
Okay. And then all the vertex labels are multiplied by 1. Then all the vertex labels are multiplied by 2. And then we take the sum of this. If it is coming to be a constant, then we can say it is a distance magic, according to you, sir. This is a...
Yes.
Huh?
That's correct. That's what I was saying.
Okay, 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 sir, okay, sir. Okay, sir. And I think PG Slater has a, and his student, Neil, he was trying to say that there was he defined capital D distance magic graphs, where he has considered D as a subset of all the distances starting from 1 to up to small d. So, for example, he has taken any subset of this and sum it, but he has not taken the product, I think. That is the way, I think it is a very new...
Definition.
Yes, sir.
Later,
yes, sir.
Choose a set D of positive integers.
Yes, sir. Yes, sir.
Okay. Then he takes all vertices whose distance is in that set.
Okay, in that set. Okay, okay.
And take the sum.
Okay.
So suppose if you say 2, 3, 5.
Yes,
then
sir.
you take all vertices with distance 2, 3, and 5 and sum it up.
Sum it. Okay, okay.
So D is fixed for him.
Okay, that is a Slater definition. Yes, sir.
That is latest general definition, D vertex magic labeling.
Yes, sir. Yes, sir. Yes, sir.
Now, this looks like it is related to distance. So this is another thing that it makes sense to call it distance magic. In fact, it makes the most sense. This looks like the best meaning for distance magic, that you pick a set of distances and you use those. Now, how is that different from just using the neighborhood? Suppose you had a graph and you picked a set D of distances. Now I'll make a new graph with the same vertex set, and every vertex in the new graph is adjacent to all the vertices at the distances given in the set D.
Okay.
So this new graph is just the original neighborhood magic graph.
Right.
Yes, yes.
So it's really the same as neighborhood magic. Maybe.
Maybe, yes.
It's a special case of neighborhood magic because the
Yes.
neighborhoods are defined in a peculiar way.
Yes.
But it's interesting to say, what kind of graphs do you get by creating the neighborhood graph? The way I said, you won't get all graphs that way, I think, or at least say, suppose you're given a graph G,
Okay.
and then for every set D,
Okay.
you get a different neighborhood graph.
Yes, 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 definitely.
And how are these related? Actually, this is related to other questions in graph theory, like the distance 2 graph or the distance 3 graph.
Okay.
So it's getting related to other concepts. There's a concept called the square of a graph, but I can never remember what it means.
Yeah.
Does anyone know?
I think a square is like this. Suppose this is a graph we have,
Yes.
and I take the vertices which are at distance 2 and join them.
Okay, that's the distance 2 graph.
So this
So
is
that would correspond to this.
this one. This will be joined to this one like that.
Correct.
Oh.
But it not distance 1. So okay, there's a concept of the distance 1 and 2 graph.
Okay, distance 1 and 2.
That's a different concept.
Okay.
And so the set D is more flexible. It includes all these concepts.
Okay. Okay.
I see. Okay, thank you. One day I'll remember this.
I think Professor Armugam, can we think about this one, sir? So if you have a graph G, what Professor Jaslavsky was suggesting that you take all the vertices at distance 1, distance 2, and so on, and then whenever you label this one and take the product of this by 1, 2, and so on, and then sum, if this turns out to be a constant, then that should be the actual distance magic labeling.
Okay, you have to fix a K.
Yes, yes, yes.
Okay. So test distance 1 to up to K, where K is fixed.
Yes, sir, yes, sir, yes, sir.
Otherwise,
Yeah.
if you K up to diameter, it becomes complete graph.
Yeah, yeah, it will be complete graph, and that we know that complete graph is not
You have
distance.
to fix the K, for example, fix 3, K equal to 3.
Yes,
Then
yes,
we go only up to distance 3 and
yes.
do so whatever is.
Yes, yes, yes. Up to
That's what.
distance K.
Yes, you can call it
That would
K
be a
distance.
bounded distance.
K
Yes,
distance.
you
This
can do
should
that.
be less than, this will be less than diameter of G.
Less than the diameter, strictly less than the diameter.
Strictly less than, yes, strictly less than the diameter.
Well, why not equal? So that's a generalization.
Become complete graph.
So if you take it equal, then it will be
everyone will be added. All vertices will get into the summation.
So it should be strictly less than.
Strictly less is better.
I think this looks very good actually, sir. If you fix K, and if K is less than diameter, definitely if it is equal to diameter, then it is a complete graph, and complete graph is known to be not distance magic.
Now, what is multiplying things by 2, 3 differently?
Differently.
Okay, that is not obvious.
That will be not always, yes, that is not obvious, but may give some idea. So,
I see what you're saying. You're saying that using Slater's rule, if you take all, D is the whole set of numbers from 1 to the diameter, then it's just like complete graph. But if you take a subset of that, like all the numbers from 1 to K in the set D, capital D, then you will get a more interesting, but that's the Slater definition.
Right.
It's a version of the Slater definition. Okay, but certainly as interesting as the original question, yes, I would think. But that's different from what I was thinking.
yeah, different.
Oh, okay, well.
This is different from the Slater definition, because here we are going to take the product of the distances also.
Correct. It seems like the distance matrix might be applicable to what I was suggesting, that you multiply the distance matrix times the label vector, and you should get a multiple of the all ones vector. That would be the criterion for having that kind of distance labeling.
We have to see, I think, how we are going to work.
That's right. Oh, it's up to you.
If you take distance matrix, and the way Professor Armugam proved the result, that if you take all unit vectors and product, then the weight will be like that one. Vertex will be defined in that manner, and I think Professor Armugam can give some clue about this one. Sir. So instead of adjacency matrix, we can take distance matrix, and then we use that same procedure. Can we get some different? I think this is different idea actually.
Well, these are all open questions then. There are lots of questions.
Yes, sir.
Okay, the next talk is at 2 o'clock.
Yes,
And
yes.
right now it is
12:40.
12:40. Oh, okay. Thank you.
Yes. Just an announcement to all the participants. The attendance link or the feedback link has been shared on the YouTube chat. Kindly fill it up. It will be accessible only for half an hour. I repeat, the feedback link has been shared on the YouTube chat, the live stream chat. Kindly fill it up. It will be accessible for half an hour. Thank you. We will break for lunch now and we will meet at 2 o'clock.